let's label it down here. So this is C equals -1. C equals -2 would be y equals x. No, what am I doing? C equals -1 is y equals x plus 2. That's right. Well, how about the other side? If C equals plus 1, well, then it's going to go through the origin. Looks like a little more room down here. How about that one must, so if this is going to be C equals 1, then I sort of get the idea. C equals 2 will look like this. They're all going to be parallel lines because all that's changing is the y-intercept as I do this thing. So here it's C equals 2. C equals, that's probably enough. All right, let's put in the line elements. All right, C equals -1. These will be perpendicular. C equals 0, like this. C equals 1. Oh, this is interesting. I can't even draw in the line elements because they seem to coincide with the curve itself, with the line itself. They lie along the line, and that makes it hard to draw them in. How about C equals 2? Well, here the line elements will be slanty. They'll have slope 2. So it's pretty slanty up. And I can see for C equals 3 in the same way, they're going to be even more slantier up. And here they're going to be even more slanty down. This is not very scientific terminology or mathematical, but you get the idea. Okay, so there's our quick version of the direction field. All we have to do is put in some integral curves now. Well, looks like it's doing this. It gets less slanty. Here it levels out, has slope 0. And now in this part of the plane, the slope seems to be rising, so it must do something like that. This guy must do something like this. I'm a little doubtful of what I should be doing here. How about going from the other side? Well, it rises, gets a little, should it cross this? What should I do? Well, there's one integral curve which is easy to see. It's this one. This line is both an isocline and an integral curve. It's everything, except drawable. So, okay, you understand this is the same line. It's both orange and pink at the same time, but I don't know what combination color that would make. It doesn't look like a line, but you know, be sympathetic. Now the question is, what's happening in this corridor? In the corridor, that's not a mathematical word either, between the isoclines for, well, what are they? They're the isocline for C equals 2 and C equals 0. How does that corridor look? Well, it's something like this. Over here, the lines are all look like that, and here they all look like this. The slope is 1, slope is 2. And a hapless solution gets in there. What's it to do? Well, do you see that if a solution gets in that corridor, an integral curve gets in that corridor, no escape is possible. It's like a lobster trap. You know, the lobster can walk in, but it cannot walk out because the things are always going in. How could it escape? Well, it would have to double back somehow, and remember, to escape, it has to be, to escape on the left side, it must be going horizontally. But how could it do that without doubling back first and having the wrong slope? The slope of everything in this corridor is positive, and to double back and escape, it would at some point have to have negative slope. It can't do that. Well, could it escape on the right-hand side? No, because at the moment when it wants to cross, it will have to have a slope less than this line, but all these spiky guys are pointing it can't escape that way either. So no escape is possible. It has to continue on there. But more than that is true. So solution can't escape. Once it's in there, it can't escape. It's like those, what do they call those plants? I forget. Pitcher plants. Pitcher plants. You know, all the hairs are going down, so it looks like that. And so when the poor little insect falls in, it could climb up the walls, except that all the hairs are going the wrong direction and it can't get over them. Well, think of it that way. This poor trapped solution. Well, so it does what it has to do. Now, there's more to it than that, and because there are two principles involved here that you should know that help a lot in drawing these pictures. Principle number one is that two integral curves cannot cross at an angle. Two integral curves can't cross I mean by crossing at an angle like that. I'll indicate what I mean by a picture like that. Now, why not? This is an important principle. Let's put that up in, at least in a white box. They can't cross because if two integral curves are trying to cross, well, one will look like this because it's an integral curve because it has this slope, and the other integral curve has this slope, and now they fight with each other. What is the true slope at that point? Well, the direction field only allows you to have one slope. If there's a line element at that point, it has a definite slope, and therefore it cannot have both this slope and that one. It's as simple as that. So you can't, the reason is you can't have two slopes. The direction field doesn't allow it. Well, that's a big, big help, because if I know here's an integral curve, and if I know that none of these other pink integral curves are allowed to cross it, how else can I do? Well, they can't escape, they can't cross. It's sort of clear that they must get closer and closer to it. You know, I'd have to work a little to justify that, but I think nobody would have any doubt of it who did a little experimentation. In other words, all these curves join that little tube and get closer and closer to this line y equals x. And therefore, without solving the differential equation, it's clear that all of these solutions, how do they behave? As x goes to infinity, they become asymptotic to, they become closer and closer to the solution x. Is x a solution? Yeah, because it's an y equals x is an integral curve. Is x a solution? Yeah, because if I plug in y equals x, I get what? On the right-hand side, I get 1, and on the left-hand side, I get 1. 1 equals 1. So this is a solution. Let's indicate that it's a solution. So analytically, we've discovered an analytic solution to the differential equation, namely y equals x, just by this geometric process. Now, there's one more principle like that, which is less obvious, but you do have to know it. And so they're not allowed to cross. That's clear. But it's much, 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 much less obvious that two integral curves cannot touch. That is, they cannot even be tangent. Two integral curves cannot be tangent. I'll indicate that by the word touch, which is what a lot of people say. In other words, if this is illegal, so is this. Can't have it. You know, without that, for example, it might be, I might feel that there would be nothing in this to prevent those curves from joining. Why couldn't these pink curves join the line y equals x? You know, it's a solution. They just hitch a ride, as it were. The answer is they cannot do that because they have to just get asymptotic to it, ever closer. They can't join y equals x, because at the point where they join, you'd have that situation. Now, why can't you have this? That's much more sophisticated than this, and the reason is because of something called the existence and uniqueness theorem. Existence and uniqueness theorem, which says that there's, through a point x0, y0, that y prime equals f of xy has only one and only one solution. One has one solution. In mathematics speak, that means at least one solution. It doesn't mean it has just one solution, okay? That's mathematical convention. It has one solution, at least one solution, but the killer is only one solution. That's what you have to say in mathematics if you want just one. One and only one solution through the point x0, y0. So the fact that it has one, that's the existence part. The fact that it has only one is the uniqueness part of the theorem. Now, like all good mathematical theorems, this one does have hypotheses. So this is not going to be a course, I warn you, those of you who are theoretically inclined, very rich in hypotheses, but you do have to, the hypotheses for this one are that f of xy should be a continuous function. Now, you know, like polynomial signs, stuff like good, should be continuous near, in the vicinity of that point. That guarantees existence, and what guarantees uniqueness is the hypothesis that you would not guess by yourself. Neither would I. What guarantees the uniqueness is that also its partial derivative with respect to y should be continuous. Should be continuous near x0, y0. Well, I have to make a decision. I don't have time to talk about Euler's method. Let me refer you to there's one page of notes, and I couldn't do any more than just repeat what's on those notes. So I'll trust you to read that, and instead let me give you an example which will solidify these things in your mind a little bit. I think that's a better course. The example is not in the notes, and therefore, remember you heard it here first. Okay, so what's the example? It's so here's our differential equation. Now let's just solve it by separating variables. dy, can you do it in your head? dy over dx, put all the y's on the left, it will look like dy over 1 minus y. Put all the dx's on the left, so the dx here goes on the right rather. That will be dx, and then the x goes down into the denominator, so now it looks like that. And if I integrate both sides, I get the log of 1 minus y, I guess maybe with a, I never bother with that, but you can. It should be absolute values, but all right, put an absolute value. Plus a constant. And now if I exponentiate both sides, the constant is positive. And so this is going to look like 1 minus y equals x. And the x constant will be e to the c1, and I'll just make that a new constant, cx. And now you can fuss by letting C be negative. That's why you can get rid of the absolute values if you allow C to have negative values as well as positive values. Let's write this in a more human form. So that's y is equal to 1 minus cx. Good. All right, let's just plot those. So these are the solutions. Pretty easy equation, pretty easy solution method. Just separation of variables. What do they look like? Well, these are all lines whose intercept is at 1. And they have any slope whatsoever. So these are the lines that look like that. Okay, now let me ask, existence and uniqueness. Existence. Through which points of the plane does a solution go? Answer. Through every point of the plane, through any point here, I can find one and only one of those lines, except for these stupid guys here on the stalk of the flower. Here, there is no, for each of these points, there is no existence. There is no solution to this differential equation which goes through any of these wiggly points on the y-axis. With one exception, this point is oversupplied. At this point, it's not existence that fails, it's uniqueness that fails. No uniqueness. There are lots of things which go through here. Now, is that a violation of the existence and uniqueness theorem? It cannot be a violation because a theorem has no exceptions, otherwise it wouldn't be a theorem. So let's take a look. What's wrong? We thought we solved it, modulo putting the absolute value signs on the log. What's wrong? The answer, what's wrong is, to use the theorem, you must write the differential equation in standard form, in that green form I gave you. Let's write the differential equation the way we were supposed to. It says dy dx equals 1 minus y divided by x. And now I see the right-hand side is not continuous, in fact, not even defined when x equals 0, when along the y-axis. And therefore, the existence and uniqueness is not guaranteed along the line x equals 0, the y-axis, and in fact, we see that it failed. Now, as a practical matter, it's the way existence and uniqueness fails in all ordinary life work with differential equations is not through sophisticated examples that mathematicians can construct, but normally because f of x, y will fail to be defined somewhere, and those will be the bad points. Thanks. Well, the topic for today is today we're going to talk, I'm postponing the linear equation to next time. Instead, I think it's a good idea, since in real life most of the differential equations are solved by numerical methods, to introduce you to those right away. Even when you see the computer, where you saw the computer screen, the solutions being drawn, of course, that what really was happening is that the computer was calculating the solutions numerically and plotting the points. So this is the main way, numerically is the main way differential equations are actually solved. If they're of any complexity at all. Now, so the problem is an initial value problem. Let's write it a first order problem the way we talked about it on Wednesday. And now I'll specifically add to that the starting point that you used when you did the computer experiments. And I'll write the starting point this way. So y of x0 should be y0. So this is the initial condition, and this is the first order differential equation. And as you know, the two of them together are called an IVP, an initial value problem, which means two things: the differential equation and the initial value that you want to start the solution at. Okay. Now, the method we're going to talk about, the basic method, of which many others are merely refinements in one way or another, is called Euler's method. Euler, who did, of course, everything in analysis, didn't, as far as I know, didn't actually use it to compute solutions of differential equations. His interest was theoretical. He used it as a method of proving the existence theorem, proving that solutions existed. But nowadays it's used to calculate the solutions numerically. And the method is very simple to describe. It's so naive. If you probably think that if you had been living 300 years ago, you would have discovered it and covered yourself with glory for all eternity. Here is our starting point, x0, y0. Now, what information do we have? At that point, all we have is the little line element whose slope is given by f of x, y. So if I start the solution, the only way the solution could possibly go would be to start off in that direction, since I have no other information. At least it has the correct direction at x0, y0, but of course it's not likely to have the correct direction anywhere else. Now, what you do then is choose a step size. I'll draw just a few, 2 steps of the method. That's, I think, good enough. You choose a uniform step size, which is usually called h. And you continue that solution until you get to the next point, which will be x0 plus h, as I've drawn it on the picture. So we get to here. We stop at that point. And now you recalculate what the line element is here. Suppose here the line element now through this point goes like that. Well, then that's the new direction that you should start out with, going from here. And so the next step of the process will carry you to here. That's 2 steps of Euler's method. Notice it produces a broken line approximation to the solution. But in fact, you only see that broken line if you're at a computer, if you're looking at the computer visual, for example, whose purpose is to illustrate for you Euler's method. In actual practice, what you see is just the computer is simply calculating this point, and the succession of points. And many programs will just automatically connect those points by a smooth-looking curve if that's what you prefer to see. Well, that's all there is to the method. What we have to do now is derive the equations for the method. Now, how are we going to do that? Well, the essence of it is how to get from the nth step to the n plus first step. So I'm going to draw a picture just to illustrate that. So now we're not at x0, but let's say we've already gotten to xn, yn. How do I take the next step? Well, I take the line element, and it goes up like that, let's say, because the slope is this. I'm going to call that slope a sub n. Of course, a sub n is the value of the right-hand side at the point xn, yn, and we'll need that in the equation. But I think it will be a little clearer if I just give it a capital letter at this point. Now, this is the new point, and all I want to know is, what are its coordinates? Well, the xn plus 1 is there. The yn plus 1 is here. Clearly, I should draw this triangle, complete the triangle. This side of the triangle, the hypotenuse has slope an. This side of the triangle has length h. H is the step size. Perhaps I better indicate that, actually put that up so that you know the word. Step size. It means It's the step size on the x-axis, how far you have to go to get from each x to the next one. What's this? Well, if that slope has this, the slope an, this is h, then this must be h times an, the length of that side, right? In order that the ratio of the height to this width should be an. And that gives us the method. How do I get from, clearly, to get from xn to xn plus 1, I simply add h. So that's the trivial part of it. The interesting thing is, how do I get the new yn plus 1? And so the best way to write it as that yn plus 1 minus yn divided by h, well, yn plus 1 minus yn is this line the same as the line h times an. So that's the way to write it. Or, since the computer is interested in calculating yn plus 1 itself, put this on the other side. You take the old yn, the previous one, and to it you add h times an. And what, pray tell, is an? Well, the computer has to be told that an is the value of f. So now, with that, let's actually write the Euler program. Not the program, but the Euler method equations. Let's just call it the Euler equations. What will they be? First of all, the new x is the old x plus h. The new y is just what I've written there. The old y plus h times a certain number an. And finally, an has the value. It's the slope of the line element here, and therefore, by definition, that's f of xn, yn. So it's these three equations which define Euler's method. If I assume in 100, surely you must be asked to, at some point, as an exercise in the term at one point, to calculate, to program the computer in C or whatever they're using, Java now, I guess, to do Euler's method. And these are the equations these would be the recursive equations that you would put in to do that. Okay, let's try an example then. So what would be a good color for Euler? Well, purple. I assume nobody can see purple. Is that correct? Can anyone in the back of the room see that's purple? What? Okay. Sit closer. So let's calculate. The example, I'll use a simple example, but it's not entirely trivial. My example is going to be the equation x squared minus y squared on the right-hand side. And let's start with y of 0 equals 1, let's say. And so this is my initial value problem, that pair of equations. And I have to specify a step size. So let's take the step size to be 0.1. You choose the step size, or the computer does. We'll have to talk about that in a few minutes. Now what do? Well, I say this is a non-trivial equation because this equation, as far as I know, cannot be solved in terms of elementary functions. So this equation would be, in fact, a very good candidate for a numerical method like Euler's. And you had to use it, or maybe it was the other way around, I forget. On your problem set, you drew a picture of the direction field and answered some questions about the isoclines, how the solutions behave. All right, now, the main thing I want you to get, this is not just for Euler's, talking about Euler's equations, but in general, for the calculations you have to do in this course, it's extremely important to be systematic, because if you are not systematic, you know, if you just scribble, 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 you can do the work, but it becomes impossible to find mistakes. You must do the work in a form in which you can check, in which it can be checked, which you can look over it, find and try to see where the mistakes are, if in fact there are any. So I strongly suggest this is not a suggestion, this is a command, that you make a little tape to do Euler's method by hand. I'd only ask you for a step or two, since I'm just trying to make sure you have some idea of these equations and where they come from. So first the value of n, then the value of xn, then the value of the yn, and then a couple of more columns which tell you what the how to do the calculation. You're going to need the value of the slope, and it's probably a good idea also, because otherwise you'll forget it, to put in HAN, because that occurs in the formula. All right, let's start doing it. Well, the first value of n is 0. That's the starting point. At the starting point, x0, y0, x has the value 0, and y has the value 1. So 0 and 1. In other words, I'm carrying out exactly what I drew pictorially, only now I'm doing it arithmetically using a table and substituting into the formulas. Okay, the next thing we have to calculate is AN. Well, since AN is the value of the right-hand side at the point 0, 1, you have to plug that in. The right-hand side is x squared minus y squared. So it's 0 squared minus 1 squared. The value of the slope there is minus 1, negative 1. Now I have to multiply that by h. H is 0.1, so it's negative. I'll never learn that. The way you learn to talk in kindergarten is the way you learn to talk the rest of your life, unfortunately. In kindergarten, we said minus. Negative 0.1. N is 1 now. What's the value of xn? Well, to the old one, I add 1/10. What's the value of y? Well, at this point, you have to do the calculation. It's the old value of y. To get this new value, it's the old value plus this number. Well, that's this plus that number is 9/10. AN, now I have to calculate the new slope at this point. Okay, that is 1/10 squared minus 9/10 squared. Gulp. That's 0.01 minus 0.81, which makes minus 0.80, I hope. Check it on your calculators. Whip them out and press the buttons. I now multiply that by h, and which means it's going to be minus 0.08. Perhaps with a 0 after. I didn't tell you how many decimal places. Let's carry it out to 2 decimal places. I think that'll be good enough. And finally, the last step, 2 here. Add another 1/10, so the value of x is now 2/10. And finally, what's the value of y? Well, I didn't tell you where to stop. Let's stop at y of let's stop at y of 0.2 because there's no more room on the blackboard. It seems like an excellent, about approximately how big is that, in other words. Then this is going to be the old y plus this number, which seems to be 0.82 to me. So the answer is the new value is 0.82. Okay, well, we got a number. We did what we were supposed to do. We got a number. Next question. Well, now let's ask a few questions. One of the first most basic thing is, how right is this? How can I answer such a question if I have no explicit formula for that solution? That's the basic problem with numerical calculation. In other words, I have to wander around in the dark to some extent and yet have some idea when I've arrived at the place that I want to go. Well, the first question I'd like to answer is this too high or too low? Is Euler, sorry, he will forgive me in heaven, I will use him by this, I mean, is the result, well, let me say something first, and then I'll criticize it. Is Euler too high or too low? In other words, is the result of using Euler's method, i.e., is this number too high or too low? Is it higher than the right answer, what it should be, or is it lower than the right answer, or, God forbid, is it exactly right? It's almost never exactly right. That's not an option. And how will we answer that question? Well, let's answer it geometrically. Basically, if the solution were a line, were a straight line, then the Euler method would be exactly right all the time. But it's not a line, then it's a curve. Well, the critical question is it curved? Is the solution? So here's the solution. Let's call it y1 of x, and let's say here was the starting point. Here the solution is convex, and here the solution is concave. Right? Concave up, a concave down, if you learn those words. But I think those have by now I hope, pretty well disappeared from the curriculum. Call it, if you haven't up till now, what mathematicians call it. Convex is that, and the other one is concave. Well, how do the Euler solutions look? Well, I'll just sketch. I think from this you can see already, when you start out on the Euler solution, it's going to go like that. Now you're too low. Well, let's suppose after that the line element here is approximately the same as what it is there. You know, roughly parallel. After all, they're not too far apart. And the direction field is continuous. That is, the directions don't change drastically from one point to another. Well, then it'll sort of, but now you see it's still too low. It's even lower as it pathetically tries to follow. It's losing territory, and that's basically because the curve is convex. Exactly the opposite would happen if the curve were concave, if the solution curve were concave. Now it's too high, and it's not going to be able to correct that as long as the solution curve stays concave. Well, that's probably too optimistic. It's probably more like this. So in other words, in this case, if the curve is convex, the Euler is going to be too high. Too low. Let's put E for Euler. How about that? Euler is too low. If it's concave, then Euler is too high. Okay, that's great. There's just one little problem left. Namely, if we don't have a formula for the solution, and we don't have a computer that's busy drawing the picture for us, in which case we wouldn't need any of this anyway, how are we supposed to tell if it's convex or concave? Back to calculus. Calculus to the rescue. When is a curve convex? A curve is convex if its second derivative is positive, because the first to be convex means the first derivative is increasing all the time, and therefore the second derivative, which is the derivative of the first derivative, should be positive. Just the opposite here. The curve, the slope is, the first derivative is decreasing all the time, and therefore the second derivative is negative. So all we have to do is decide what the first and what the derivative, the second derivative of this solution is. We should probably call it a solution. To y of x is a little too vague. y1 means the solution that started at this point. So in fact, probably it would have been better from the beginning to call that y1, except there's no room. y1, let's say. That means the solution which started out at the point 0, 1. So I'm still talking about a solution like that. All right. So I want to know if this is positive, the second derivative is positive at the starting point 0, or it's negative. Now, again, how do you calculate the second derivative if you don't know what the solution is explicitly? And the answer is you can do it from the differential equation itself. How do I do that? Well, easy. Y prime equals x squared minus y squared. Okay, that tells me how to calculate y prime. if I know the value of x and y, in other words, the point 0, 1. What would be the value of y double prime? Well, differentiate the equation. It's 2x minus 2y y prime. Don't forget to use the chain rule. So if I want to calculate at 0, 1, in other words, if my starting point is that curve convex or concave, well, let's calculate. Y of 0 equals 1. Okay, what's y prime of 0? Well, I don't have to repeat that calculation. Using this, I already calculated that it was negative 1. And now the new thing is, what's y double prime of 0? Well, it is this. It is, I'll write it out. It's 2 times 0 minus 2 times negative y, which is 1, 2 times 1 times y prime, which is negative 1. You want to see we're pulling ourselves up our own bootstraps, which is impossible, but it is not impossible because we're doing it. So what's the answer? 0 here, 2. I've calculated without having the foggiest idea of what the solution is or how it looks. I've calculated that its second derivative at the starting point is 2. Therefore, my solution is convex at the starting point, and therefore this Euler approximation, if I don't carry it out too far, will be too low. So it's convex, Euler, too low. Now, you could argue, well, what about this? You know, suppose it, you know, yeah, you know, so you go like this, and but then it, see, it catches up, and then so, well, of course, if the curve changes from convex to concave, then it's really impossible to make any prediction at all. That's a difficulty. So all this analysis is only if you stay very nearby. However, I wanted to show you, the main purpose of it in my mind was to show you how to use it's these equations, how to use the differential equation itself to get information about the solutions without actually being able to calculate the solutions. Now, so that's the method, and that's how to find out something about it. And now what I'd like to talk about is errors. How do I handle, right. So, I mean, that's in a sense, I've started the error analysis. In other words, the error, by definition, the error is this difference, E. The error between. So in other words, I'm asking here, is the error positive? As it would be, it depends which way you measure it. Usually you take this minus that. So here the error would be considered positive, and here it would be considered negative, although I'm sure there's a book somewhere in the world which does the opposite. Most hedge by just using the absolute value of the error, plus a statement that the method is producing answers which are too low or too high. The question then is, naturally, this is not the world's best method. It's not as bad as it seems. It's not the world's best method because that convexity and concavity means that you're automatically introducing a systematic error. If you can predict which way the error is going to be by just knowing whether the curve is convex or concave, then it's not what you want. I mean, you want to at least have a chance of getting the right answer, whereas this is telling you you're definitely going to get the wrong answer. All it tells you is, and it's telling you because your answer is going to be too high or too low. We'd like a better chance of getting the right answer. Now, so the question is, how do you get a better method? A search is for a better method. Now, the first method which will occur, I'm sure, to anyone who looks at that picture is, look, if you want this yellow line to follow the white one, the white solution more accurately, for heaven's sake, don't take such big steps. Take small steps, and then it will follow better. All right, let's draw a picture. Excuse me. My little box of treasures here. Take anywhere away. So, use a smaller step size. And the picture roughly which is going to justify that will look like this. If the solution curve looks like this, then with a big step size, I'm liable to have something that looks like that. But if I take a smaller step size, suppose I have the step size, how is it going to look then? Well, I better switch to a different color. If I have the step size, I'll get a littler. It goes like that, and now it's following closer. Of course, I'm stacking the deck, but see how close it follows? You know, I'm definitely not to be trusted on this, but there. Okay, let's do the opposite, make a really big step. Suppose instead of the yellow one, I'd use the green one. Well, a double step size. Well, what would have happened then? Well, I've started out, but now I've gone all the way to there. And now on my way up, of course, it has a little further to go. But if for some reason I had stopped there, you could see I would be still lower. In other words, the bigger the step size, the more the error. And where are the errors that we're talking about? Well, the way to think of the error is this is the error. That number, the error, and you can make it a positive, negative, or just put automatically an absolute value sign around it. That's not so important. So in other words, the conclusion is that the error E, the difference between the true value that I should have gotten and the Euler value that the calculation produced, the error E depends on the step size. Now, how does it depend on the step size? Well, it's impossible to give an exact formula, but there's an approximate answer which is by and large true. And the answer is, so E is going to be a function of H. What function? Well, asymptotically, which means is another way of putting quotation marks around what I say. It's going to be a constant, some constant, times H.
Don't be late. It's you, pretty boy.
Nobody wants to take care. It looks like this, and for this reason, it's called a first order. The Euler is a first order method. And now, first order does not refer to the first order of the differential equation. It's not that use of the word first. It's not the first order because it's y prime equals f of x, y. The first order means the fact that h occurs to the first power. The way people usually say this is, since the normal way of decreasing the step size, as you'll see as soon as you try to use the computer visual that deals with the Euler method, which I highly recommend, by the way, so highly recommended that you have to do it, is that the way to say it, that since you each new step halves the step size, that's the usual way to do it. If you have the step size, since this is a constant, if I have the step size, I have the error, approximately. Have the step size, have the error. That tells you how the error varies with step size for Euler's method. Please understand, that's what people say, and please understand the grammatical construction. Since everyone in the math department has a cold these days, except me for the moment, everyone goes around chanting this mantra. This is totally irrelevant. Total mantra, you know, feed a cold, starve a fever. And if you ask them what it means, they say it means, you know, eat a lot if you have a cold, and if you have a fever, don't eat very much, which is not what it means at all. Grammatically, it's exactly the same construction as this. What this means is, if you have the step size, you will have the error. And that's what feed a cold, starve a fever means. And remember this for the rest of your life. If you feed a cold, if you eat too much when you have a cold, you will get a fever and end up having to starve yourself, because, of course, nobody, when you have a fever, nobody feels like eating, so they don't eat anything. All right? You got that? You got that. Good. Good. Go home. There you go. I want all of you to go home and tell that to your mothers. You know, that's the way we always used to speak back, you know. A grimmer one, spare the rod and spoil the child, does not mean that you should not hit your kid. And it means that if you fail to hit your kid, he or she will be spoiled, whatever that means. So you don't want to do with that. I guess the mantra today would be what? I don't know. Okay. So the first line of defense is simply to keep having the step size in Euler. And what people do is, if they don't want to use anything better than Euler's method, is you keep having the step size until the curve doesn't seem to change anymore. And then you say, well, that must be the solution. And I ask you on the problem set, how much would you continue to have the step size in order for that good thing to happen? However, there are more efficient methods which gets the result faster. And so if that's our good method, let's call this a still better method. The better methods aim at being better. They keep the same idea as Euler's method, but they say, look, let's try to improve that slope AN. In other words, since the slope AN that we start with is guaranteed to be wrong if the curve is convex or concave, can we somehow correct it so that, for example, instead of immediately aiming there, can't we somehow aim it so that by luck the next step just lands us back on the curve again? In other words, we're sort of looking for the short path, a shortcut path, which by good luck will end us up back on the curve again. And all the improvements, the simple improvements on Euler method, and they are the most stable in ways to solve differential equations numerically, aim at finding a better slope. So they find a better value for a better slope, find a better value for than AN. Try to improve that slope that you found. Now, once you have the idea that you should look for a better slope, it's not very difficult to see what, in fact, you should try. Again, I think most of you would say, hey, I would have thought of that. And you'd be closer in time, since these methods were only found about maybe 100, around the turn of the last century is when I placed them. Mostly by some German mathematicians interested in solving equations numerically. All right, so what is the better method? Our better slope. What should we look for in our better slope? Well, the simplest procedure is once again, we're starting from there, and the Euler's slope would be the same as the line element. So the line element looks like this, and our yellow slope, AN, I'll still continue to call it AN, goes like that and gets to here. Okay, now if it were convex, if the curve were convex, this would be too low, and therefore the next step would be, I'm going to draw this next step in pinks. Well, let's continue in here. Would be going up like that. I'll call this BN just because it's the next step of Euler's method. It could be called AN prime or something like that, but this will do. And now what you do is, let me put an arrow on it to indicate parallelness. Go back to the beginning. Draw this parallel to BN. So here is BN. Again, just a line of slope, that same slope. And now what you should use as the simplest improvement on Euler's method is take the average of these two, because that's more likely to hit the curve than AN will, which is sure to be too low if the curve is convex. In other words, use this instead. Use that. So this is our better slope. Okay, what will we call that slope? We don't have to call it anything. What would the equations for the method be? Well, xn plus 1 is gotten by adding the step size. So here's my step size, just as it was before. Just as it was before, the new thing is how to get the new value of y. So yn plus 1 should be the old yn plus h times not this crummy slope an, but the better, the pink slope. What's the formula for the pink slope? Well, let's do it in two steps. It's the average of an and bn. Hey, but you didn't tell me, or I didn't tell you what bn was. So you now must tell the computer, oh yes, by the way, you remember that an was what it always was. The interesting thing is, what is bn? Well, to get bn is the slope of the line element at this new point. Now, what am I going to call that new point? I don't want to call this y value yn plus 1, because it's this up here that's going to be the yn plus 1. All this is a temporary value used to make another calculation, which will then be combined with the previous calculations to get the right value. Therefore, give it a temporary name. That point, we'll call it, it's not going to be the final, the real yn plus 1. We'll call it yn plus 1 twiddles, yn plus 1 temporary. And what's the formula for it? Well, it's just going to be what the Euler formula, original Euler formula, it's going to be yn plus what you would have gotten if you had calculated. In other words, it's the point that the Euler method produced, but it's not finally the point that we want. Now, do I have to say anything else? Yeah, I didn't tell the computer what bn was. Okay, bn is the slope of the direction field at the point n plus 1, and the computer knows what that is, and this point yn plus 1 temporary. So you make a temporary choice of this, calculate that number, and then go back and, as it were, correct that value to this value by using this better slope. Now, that's all there is to the method, except I didn't give you its name. Well, it has 3 names, 4 names, in fact. Which one shall I give you? I don't care. Okay. The shortest name is Hoyne's method, but nobody pronounces that correctly. So it's Hoyne's method. It's called also the improved Euler method. It's called modified Euler. Very expressive word. Modified Euler's method, and it's also called RK2. I'm sure you'll like that name best. It has a Star Wars sort of sound to it. RK stands for Runge-Kutta. And the reason for the 2 is not that it uses two, well, it is that it uses 2 slopes, but the real reason for the 2 is that it is a second-order method. So that's the most important thing to put down about it. It's a second-order method, whereas Euler's was only a first-order method. So this is so Hoyne's method, or RK2, let's write it, that's the shortest thing to write, is a second-order method, meaning that the error varies with the step size like some constant, it won't be the same as the constant for Euler's method, times h squared. That's a big saving, because it now means that if you have the step size, you're going to decrease the error by a factor of 1/4. You will quarter the error. Now, you say, hey, great, why should anyone use anything else? Well, think a little second. The real thing which determines how slowly one of these methods run is you look at the hardest step of the method and ask how long does the computer take, how many of those hardest steps are there. Now, the answer is the hardest step is always the evaluation of the slope, the evaluation of the function. Because, you know, the functions that are in common use are not x squared minus y squared. They take half a page and have as coefficients, you know, 10 decimal place numbers, whatever the guy, the engineers doing it, you know, whatever their accuracy was. So the thing that controls how long a method runs is how many times the slope, the function, must be evaluated. For Euler, I only have to evaluate it once. Here I have to evaluate it twice. Now, roughly speaking, the number of function evaluations will give you the exponent. The method that's called Runge-Kutta 4th order will require 4 evaluations of slope, but the accuracy will be like h to the 4th. Very accurate. You have the step size, and it goes down by a factor of 16. Great. But you had to do it you had to evaluate the slope 4 times. Suppose instead you had halved 4 times this thing. And what would you have done? You would have decreased it to 1/16 of what it was. You would increase the number of functions evaluations you needed to 4, and you would have decreased the error by a 1/16. So in some sense, it really doesn't matter whether you use a very fancy method which requires more function evaluations. It's true, the error goes down faster, but you're having to do more work to get it. So anyway, nothing's free. Now, there is an RK4. I think I'll skip that since I wouldn't dare to ask you any questions about it. But I just mention it at least because it's the standard. It uses 4 evaluation. It's the standard method if you don't want to do anything fancier. It's rather inefficient, but it's very accurate. Standard method, accurate. And you'll see when you use the programs, it's in fact the program which is drawing those curves, the numerical method which draws all those curves that you believe in on the computer screen is the RK4 method. The Runge-Kutta, I should give them their names. Runge-Kutta 4th order method. I believe both German mathematicians around the turn of the last century. Runge-Kutta 4th order method requires 4 slopes. Requires you to calculate 4 slopes. I won't bother telling you what you do, but it's a procedure like that. It's just a little more elaborate. And you take 2 of these, you make up a weighted average for the super slope. You use weighted average. What should I divide that by to get the right 6? Why 6? Well, because if all these numbers were the same, I'd want it to come out to be whatever that common value was. Therefore, you always must divide by, in a weighted average, you must always divide by the sum of the coefficients. So this is the superslope. And if you plug that superslope in to here, you will be using the Runge-Kutta method and get the best possible results. Now, I wanted to spend the last 3 minutes talking about pitfalls of numerical computation in general. One pitfall I'm leaving you on the homework to discover for yourself. Don't worry, it won't cause you any grief. It'll just destroy your faith in these things for the rest of your life, which is probably a good thing. So, pitfalls. Number one, you'll find. Let me talk instead briefly about number two, which I'm not giving you an exercise in. Number two is illustrated by the following equation. What could be simpler? This is a very bad equation to try to solve numerically. Now, why? Well, because if I separate variables, why don't I save a little time? I'll just tell you what the solution is, okay? Obviously, you separate variables. Maybe you can do it in your head. The solution will be, the solutions will have an arbitrary constant in them, and they won't be very complicated. They will be 1 over c minus x. C is an arbitrary constant, and as you give different values, you get... Now, what do those guys look like? Okay, so here I am. I'm start out at the point 1, and I tell the computer, compute for me the value of the solution at 1, starting out at 1, and it computes and computes a little while. But the solution, how does this curve actually look? So in other words, suppose I say that y of 0 equals 1, find me y of 2. In other words, take a nice small step size, use the Runge-Kutta fourth order method, calculate a little bit, and tell me, I just want to know what y of 2 is. Well, what is y of 2? Oh, well, unfortunately, how does that curve look? The curve looks like this. At that point, it drops to infinity, in a manner of speaking, and then sort of comes back up again like that. What is the value of y? This is the point 1. What is the value of y of 2? Is it here? Is it this? Well, I don't know, but I do know that the computer will not find it. The computer will follow this along and get lost in eternity, in infinity, and see no reason whatever why it should start again on this branch of the curve. Okay, well, can't we predict that that's going to happen somehow and, avoid it? What I should have, the whole difficulty is this is called a singular point. This solution has a singularity. In other words, a place where it goes to infinity or becomes discontinuous, maybe has a jump discontinuity. It has a singularity at x equals c. This in particular at x equal 1 here. But from the differential equation, where is that c? There is no way of predicting it. Each solution, in other words, to this differential equation has its own private singularity, which only it knows about and where it's going to blow up, and there's no way of telling from the differential equation where that's going to be. That's what makes one of the things that makes numerical calculation difficult, when you cannot predict where things are going to go bad in advance. It's time we started solving differential equations. This is the third lecture of the term, and I have yet to solve a single differential equation in this class. Well, that will be rectified from now till the end of the term. So once you learn separation of variables, which is the most elementary method there is, I think the single most important equation is the one that's called the first order linear equation, both because it occurs frequently in models because it's solvable, and I think that's enough. If you drop the course after today, you'll still have learned the most two important methods: separation of variables and first-order linear equations. So what does such an equation look like? Well, I'll write it in, there are several ways of writing it, but I think the most basic is this. I'm going to use x as the independent variable because that's what your book does, but in the applications it's often t, time, that's the independent variable, and I'll try to give you examples which show that. So the equation looks like this. Some function of x times y prime plus some other function of x times y is equal to yet another function of x. Obviously, the x doesn't have the same status here that y does, so y is extremely limited how it can appear in the equation, but x can be pretty much arbitrary in those places. So that's the equation we're talking about, and I'll put it up. This is the first version of it, and we'll call them purple. Now, why is that called a linear equation? The word linear is a very heavily used word in mathematics, science, and engineering. For the moment, the best simple answer is because it's linear in y and y prime, the variables y and y prime. Well, y prime is not a variable. Well, you'll learn in a certain sense it helps to think of it as one, not right now perhaps, but think of it as linear by the most closely analogous thing would be the equation, a linear equation that looked like a real linear equation, the kind you studied in high school, which would look like this. It would have two variables and, I guess, constant coefficients equal c. Now, that's a linear equation, and that's the sense in which this is linear. It's linear in y prime and y, which are the analogs of the variables y1 and y2. A little bit of terminology. If c is equal to 0, it's called homogeneous, the same way this equation is called homogeneous, as you know from 1802, if the right-hand side is 0. So c of x I should write here, but I won't. That's called homogeneous. Now, this is a common form for the equation, but it's not what's called standard form. The standard form for the equation, and since this is going to be a prime course of confusion, which is probably completely correct, but a prime source of confusion is what I meant. The standard linear form, and I'll underline linear, is the first coefficient of y prime is taken to be 1. So if I divide, you can always convert that to a standard form by simply dividing through by it. And if I do that, the equation will look like y prime plus, now it's common to not call it b anymore, the coefficient, because it's really b over a, and therefore it's common to adopt yet a new letter for it, and the standard one that many people use is p. How about the right-hand side? We need a new letter for that too. It's c over a, but we'll call it q. So when I talk about the standard linear form for a linear first-order equation, it's absolutely that I'm talking about. Now, you immediately see there's a potential for confusion here, because what did I call the standard form for a first-order equation? So I'm going to say not this. The standard first-order form what would that be? Well, it would be y prime equals and everything else on the left-hand side. So it would be y prime, and now if I turn this into the standard first-order form, it would be negative p of x, y, plus q of x, but of course nobody would write negative p of x, so now I explicitly want to say that this is a form which I will never use for this equation, although half the books in the world do. In short, this poor little first order equation belongs to two ethnic groups. It's both a first order equation, and therefore its standard form should be written this way, but it's also a linear equation, and therefore its standard form should be used this way. Well, it has to decide, and I have decided for it. It is above all a linear equation, not just a first order equation, and in this course, this will always be the standard form. Now, well, what on earth is the difference? Oh, if you don't do it that way, the difference is entirely in the sign of p, but if you get the sign of p wrong in the answers, it's just disaster from that point on. A trivial little change of sign in the answer produces solutions and functions which have totally different behavior, and you're going to be really lost in this course. So maybe I should draw a line through it to indicate, please don't pay any attention to this whatsoever. Except that we're not going to do that. Okay? Well, what's so important about this equation? Well, number one, it can always be solved. That's a very, very big thing in differential equations. But it's also the equation which arises in a variety of models. Now, I'm just going to list a few of them. All of them, I think you will meet in either in part one or part two of problem sets over these first couple of problem sets, or second and third maybe. But of them, I'm going to put at the very top of the list what I'll call here, I'll give it two names, the temperature diffusion model. Well, I'm sorry, it would be better to call it temperature concentration by analogy. Temperature concentration model. There's the mixing model, which is hardly less important. In other words, it's almost as important. You have that on your problem set. And then there are other slightly less important models. There's the model of radioactive decay. There's a model of a bank interest, bank account. Various motion models. You know, Newton's law type problems, if you can figure out a way of getting rid of the second derivative. Some motion problems. A classic example is the motion of a rocket being fired off, et cetera, et cetera, et cetera. Now, today I have to pick a model, and the one I'm going to pick is this temperature concentration model. So this is going to be today's model. Tomorrow's model in the recitation, I'm asking the recitations to, among other things, make sure they do a mixing problem. To show A, to show you how to do it, and B, because it's on the problem set, so that's not a good reason, but it's not a bad one. The others are either in part one, or we'll take them up later in the term. This is not going to be the only lecture on the linear equation. There'll be another one next week of equal importance, but we can't do everything today. So let's talk about the temperature concentration model, except I'm going to change its name to the conduction diffusion model. I'll put conduction over there and diffusion over here, let's say. Since, as you'll see, the similarities, or they're practically the same model, all that's changed from one to the other is the name of the ideas. In one case you call it temperature, and the other case you call it concentration, but the actual mathematics isn't identical. But so let's begin with conduction. All right, here's I need a simple physical situation that I'm modeling. So imagine a tank of some liquid. Water will do as well as anything. And in the inside is suspended somehow is a chamber. A metal cube will do. And let's suppose that its walls are partly insulated. Not so much that no heat can get through. There is no such thing as perfect insulation anyway, except maybe a perfect vacuum. Now, inside, so here on the outside is liquid. Okay. On the inside is what I'm interested in is the temperature of this thing. I'll call that T. Now, that's different from the temperature of the external water bath, so I'll call that T sub E. T for temperature, measured in Celsius, let's say, for the sake of definiteness. But this is the external temperature, so I'll indicate it with an E. Now, what is the model? Well, in other words, how do I set up a differential equation to model this situation? Well, it's based on a physical law, which I think you know. You've had simple examples like this. The so-called Newton's law of cooling. Which says that the rate of change, the temperature, the heat goes from the outside to the inside by conduction only. Heat, of course, can travel in various ways, by convection, by conduction as here, or by radiation are the three most common. Of these, I only want one, namely transmission of heat by conduction. And that's the way it's probably a little better to call it the conduction model rather than the temperature model, which might be involve other ways for the heat to be traveling. So dt, the independent variable is not going to be x as it was over there. It's going to be t for time. So maybe I should write that down. T equals time, capital T equals temperature in degrees Celsius, and you put in the degrees Celsius if you want. So it's proportional to the temperature difference between these two. Now, how shall I write the difference? Write it this way, because if you don't, you'll be in trouble. Now, why do I write it that way? Well, I write it that way because I want this constant to be positive, a positive constant. In general, any constants or parameters which are physical, have some physical significance, one always wants to arrange the equation so that they're positive numbers, the way people normally think of these things. This is called the conductivity. The conductivity of what? Well, I don't know, of the system, of the situation. The conductivity of the wall, or if the metal were just by itself, it would, at any rate, it's a constant. It's thought of as a constant. And why positive? Well, because if the external temperature is bigger than the internal temperature, I expect T to rise, the internal temperature to rise. That means dt, its slope, should be positive. So in other words, if TE is bigger than T, I expect this number to be positive. And that tells you that K must be a positive constant. If I had turned it the other way, expressed the difference in the reverse order, K would then be negative, have to be negative in order that this turn out to be positive. in that situation I described. And since nobody wants negative values of k, you have to write the equation in this form rather than the other way around. So there's our differential equation. It will probably have an initial condition, so it could be the temperature at the starting time should be some given number T0. But the condition could be given in other ways. One could ask, what's the temperature as time goes to infinity, for example? There are different ways of giving that initial condition. Okay, that's the conduction model. What would the diffusion model be? The diffusion model mathematically would be word for word the same. The only difference is that now what I imagine is, I'll draw the picture the same way, except now I'm going to label the inside not with a T but with a C. C for concentration. It's in an external water bath, let's say, so there's an external concentration. And what I'm talking about is some chemical, let's say salt will do as well as anything. So C is equal to salt concentration inside, and CE would be the salt concentration outside in the water bath. Now, I imagine some mechanism. So this is a salt solution, that's a salt solution, and I imagine some mechanism by which the salt can diffuse. It's a diffusion model now. Diffuse from here into there, or possibly out the other way, and that's usually done by vaguely referring to that the outside is a semi-permeable membrane. Semi-permeable so that the salt will have a little hard time getting through, but permeable so that it won't be blocked completely. So there's a membrane, you write the semi-permeable membrane outside the inside. Well, I give up. You know, not membrane somewhere. Sorry. Membrane wall. How's that? Now, what's the equation? Well, the equation's the same, except it's called the diffusion equation. I don't think Newton got his name on this. The diffusion equation says that the rate at which the salt diffuses across the membrane, which is the same up to a constant as the rate at which the concentration inside changes, is some constant, usually called K still. Okay. Do I contradict? Yeah, well, okay. Let's keep calling it K1. Now it's different. Times CE minus C. And for the same reason as before, if the external concentration is bigger than the internal concentration, we expect salt to flow in. That will make C rise. It will make this positive, and therefore we want K to be positive, just K1 to be positive for the same reason it had to be positive before. So in each case, the model that I'm talking about is the differential equation. So maybe I should, let's make that clear. Or I would say that this first order differential equation models this physical situation, and the same thing is true on the other side, over here. This is the diffusion equation, and this is the conduction equation. Now, if you were in any doubt about the power of differential equations, the point is, when I talk about this thing, I don't have to say which of these I'm following. I'll use neutral variables like y and x to solve these equations, but clearly with a single stroke, I will be handling both situations together, and that's the power of the method. Now, you obviously must be wondering, look, hey, these look very, very special. He said he was going to talk about the general first order equation, but these look rather special to me. Well, not too special. How shall we write it? Suppose I'll write it let's take the temperature equation just to have something definite. Notice that it's in a form corresponding to Newton's law, but it is not in the standard linear form. Let's put it in standard linear form, so at least you can see that it's a linear equation. So if I put it in standard form, it's going to look like dt dt, d little t, plus kt is equal to k times te. Now compare that with the way the general equation is supposed to look, that yellow box over there, the standard linear form. How are they going to compare? Well, this is a pretty general function. This is a general function of t, because, you know, I can make the external temperature, I can suppose it behaves in any way I like. Steadily rising, decaying exponentially, maybe oscillating back and forth for some reason. The only way in which it's not general is that this k is a constant. So I will ask you to be generous. Let's imagine the conductivity is changing over time. So this is usually constant, but there's no law which says it has to be. How could a conductivity change over time? Well, we could suppose, for example, that this wall was made of slowly congealing jello, for instance. You know, it starts out as liquid, then it gets solid, and jello doesn't transmit heat, I believe, quite as well as liquid does, as a liquid would. Is jello a solid or a liquid? I don't know. Let's forget about that. So with this understanding, so let's say not necessarily here, but not necessarily, I can think of this, therefore, by allowing k to vary with time and the external temperature to vary with time. I can think of it as a general linear equation. So these models are not special, they're fairly general. Well, I did promise you I would solve an equation, and in this lecture I still have not solved any equations. Okay, time to stop temporizing and solve. So I'm going to, in order not to play favorites with these two models, I'll go back to, and to get you used to thinking of new variables all the time, that is, you know, being eclectic, switching from one variable to another according to which particular lecture you happen to be sitting in. So let's take our equation in the form y prime plus p of xy, the general form, using the old variables, equals q of x. Solve me. Well, there are different ways of describing the solution process. No matter how you do it, it amounts to the same amount of work. And there's always a trick involved in each one of them, since you can't suppress a trick by doing the problem some other way. The way I'm going to do it, I think, is the best. That's why I'm giving it to you. It leads to, it's the easiest to remember, leads to the least work, but I have colleagues who would fight with me on that point. So, since they're not here to fight with me, I am free to do whatever I like. One of the main reasons is that of doing it the way I'm going to do is because I want you to get one more word into your consciousness, and that's the word, two words, integrating factor. I'm going to solve this equation by finding an integrating factor of the form u of x. What's an integrating factor? Well, I'll show you, not by writing an elaborate definition on the board, but showing you what its function is. It's a certain function u of x. I don't know what it is, but here's what I want it to do. I want to multiply, I'm going to drop the x's just so that the thing looks less complicated. So what I want to do is multiply this equation through by u of x. That's why it's called a factor, because you're going to multiply everything through by it. So it's going to look like uy prime plus pu y equals qu. And now this thing is, so far it's just a factor. What makes it an integrating factor is that this, after I do that, I want this to turn out to be the derivative of something with respect to x. You see the motivation for that? If this turns out to be the derivative of something because I've chosen u so cleverly, then I'll be able to solve the equation immediately just by integrating this with respect to x and integrating that with respect to x. You just then integrate both sides with respect to x and the equation is solved. Now, the only question is, what should I choose for u? Well, if you think of the product formula, there might be many things to try here, but there's only one reasonable thing to try. Try to pick u so that it's the derivative of u times y. See how reasonable that is. If I use the product rule on this, the first term is u times y prime. The second term would be u prime times y. Well, I've got the y there, so this will works if what? If, what's the condition that u must satisfy in order for that to be true? Well, it must be that after I do the differentiation, u prime turns out to be p times u. So is it clear? This is something we want to be equal to, and the thing I'll try to do it is by choosing u in such a way that this equality will take place, and then I'll be able to solve the equation. And now, so here's what my u prime must satisfy. Hey, we can solve that, but please don't forget that p is p of x. It's a function of x. So if you separate variables, I'm going to do this. So what is it? du over u equals p of x times dx. If I integrate that, so separate variables, integrate, and you're going to get du over u integrates to be the log of u, and the other side integrates to be the integral of p of x dx. And you can put an arbitrary constant there, or you can think of it as already implied by the indefinite integral. Well, that doesn't tell us yet what u is. What should u be? Notice I don't have to find every possible u which works. All I'm looking for is one. All I want is a single u which satisfies that equation. Well, u equals the integral e to the integral of p dx. That's not too beautiful looking, but by differential equations, things can get so complicated that by the, in a week or two, you will think of this as an extremely simple formula. So there's the formula for our integrating factor. We found it. We'll always be able to write an integrating factor. Don't worry about the arbitrary constant because you only need one such u. So no arbitrary constant since only one u needed. And that's the solution, the way we solve the linear equation. Okay, let's take over and actually do it. I think it would be better to summarize it as a clear-cut method. So let's do that. So what's our method? It's the method for solving y prime plus py equals q. Well, the first place, make sure it's in standard linear form. If it isn't, you must put it in that form. Notice the formula for the integrating factor. The formula for the integrating factor involves p, the integral of p dx, so you better get the right p. Otherwise, you're sunk. Okay, so put it in standard linear form. That way you'll have the right p. Notice that if you wrote it in that form, and all you remembered was integral e to the integral p dx, the p would have the wrong sign. If you're going to write that p should have a negative sign there. So do it this way and no other way. Otherwise you'll get confused and get wrong signs, and as I say, that will produce wrong answers, and not just slightly wrong answers, but disastrously wrong answers from the point of view of the modeling, if you really want answers to physical problems. So here's a standard linear. Then find the integrating factor. So calculate e to the integral p dx, the integrating factor. And then multiply both. I'm putting this as both. Underline that as many times as you have room in your notes. Multiply both sides by this integrating factor by e to the integral p dx. And then integrate. Okay, let's take a simple example. Suppose we started with the equation xy prime minus y equals, I had a x squared, x cubed, something like that. X cubed, I think. Yeah, x cubed. Okay. What's the first thing to do? Put it in standard form. So step 0 will be to write it as y prime minus 1 over x times y equals x squared. There are two standard errors. Let's do the work first, and then I'll talk about mistakes. And now what? Well, we now calculate the integrating factor. So that's, I would do it in steps. You can integrate negative 1 over x, right? That integrates to minus log x. So the integrating factor is e to the integral of this dx, so it's e to the negative log x. Now in real life, that's not the way to leave that. What is e to the negative log x? Well, think of it as e to the log x to the minus 1. Or in other words, it is e to the log x is x, so it's x to the minus, so it's 1 over x. So the integrating factor is 1 over x. Okay? Multiply both sides by the integrating factor. Both sides of what? Both sides of this, the equation written in standard form, and both sides. So it's going to be 1 over x y prime minus 1 over x squared y is equal to x squared times 1 over x, which is simply x. Now, if you have done the work correctly, you should be able now to integrate the left-hand side directly. So I'm going to write it this way. I always recommend that you put in as an extra step, well, I won't. Put in as an extra step the reason for using that integrating factor. In other words, that the left-hand side is supposed to be now 1 over x times y prime. I always put in that because there's always a chance you made a mistake or forgot something. Look at it, mentally differentiate it using the product rule just to check that in fact it turns out to be the same as the left-hand side. So what do we get? 1 over x times y prime plus y times the derivative of 1 over x, which indeed is negative 1 over x squared. And now finally, that's 3a. Continue, do the integration. So you're going to get, let's see if we can do it all on one board. 1 over x times y is equal to x plus a constant, x squared over 2 plus a constant. And the final step will be, therefore, I now want to isolate y by itself. So y will be equal to, multiply through by x cubed over 2 plus c times x. And that's the solution. Okay, let's do one a little slightly more complicated. Let's try this one. Now my equation is going to be 1. I'll still keep 2, y and x as the variables. I'll use t in a minute or two. 1 plus cosine x. So I'm not going to give you this one in standard form either. Trick question. Y prime minus sine x times y is equal to anything reasonable, I guess. I think what x 2x. Make it more exciting. Okay. Now, I think I should warn you where the mistakes are, just so that you can make all of them. So this is mistake number 1. You don't put it in standard form. Mistake number 2, generally people can do step 1 fine. Mistake number 2 is you don't. This is my most common mistake, so I'm very sensitive to it. But that doesn't mean if you make it, you'll get any sympathy from me. I don't give sympathy to myself. You're so intent on, so happy at having found the integrating factor, you forget to multiply q by the integrating factor also. You just handle the left-hand side of the equation, and you forget about the right-hand side. So the emphasis on the both here is the right hand, please include the q. Please include the right-hand side. Any other mistakes? Well, nothing that I can think of. Oh, maybe only. Anyway, we're not going to make any mistakes for the rest of this lecture. So what do? We write this in standard form. So it's going to look like y prime minus sine x divided by 1 plus cosine x times y equals, my heart sinks because I know I'm supposed to integrate something like this, and boy, that's going to give me problems. Okay, well, not yet. What's the integrating factor? The integrating factor is, well, we want to calculate the integral of negative sine x over 1 plus cosine. That's the integral of p dx. And after that, we have to exponentiate it. Well, can you do this? Yeah, but if you stare out a little while, you can see that the top is the derivative of the bottom. That is great. That means it integrates to be the log of 1 plus cosine x. Is that right? 1 over 1 plus cosine x times the derivative of this, which is negative cosine x. Therefore, the integrating factor is e to that. In other words, it is 1 plus cosine x. Therefore, so this was step 0. Step 1, we found the integrating factor. And now step 2, we multiply through by the integrating factor. And what do we get? We multiply through the standard form equation by the integrating factor. And if you do that, what you get is, well, y prime gets the coefficient 1 plus cosine x. Y prime minus sine x equals 2x. Oh dear. Well, I hoped somebody would giggle at this point. What's giggleable about it? Well, that all this was totally wasted work. That's called spinning your wheels. No, it's not spinning your wheels. It's doing what you're supposed to do and finding out that you wasted the entire time doing what you were supposed to do. Well, we get, in other words, the net effect of this is to end up with the same equation we started with. But what is the point? The point is of having done all this was because now the left-hand side is exactly the derivative of something, and the left-hand side should be the derivative of what? Well, it should be the derivative of 1 plus cosine x times y, all prime. Now, you can check that that's in fact the case. It's 1 plus cosine x, y prime, plus minus sine x, the derivative of this side, times y. So if you had thought, in looking at the equation, to say to yourself, this is the derivative of that, maybe I'll just check right away to see if it's the derivative of 1 plus cosine x sine y, you would have saved that work. Well, you don't have to be brilliant or clever or anything like that. You do it, you can follow your nose, and it's just, I want to give you a positive experience in solving linear equations, not too negative. Anyway, so we got to this point. So this is 2x, and now we're ready to solve the equation, which is, the solution now will be 1 plus cosine x times y is equal to x squared plus a constant, and so y is equal to x squared divided by x squared plus a constant divided by 1 plus cosine x. Suppose I had given you an initial condition, which I didn't, but suppose the initial condition said that y of 0 were 1, for instance. Then the solution would be, so this is an if, I'm throwing in at the end just to make it a little bit more of a problem. How would I then I could evaluate the constant by using the initial condition. What would it be? This would be, on the left-hand side, 1. On the right-hand side would be c over 2. So I would get 1 equals c over 2. Is that correct? Cosine of 0 is 1, so that's 2 down below. Therefore, c is equal to 2, and that would then complete the solution. It would be x squared plus 2 over 1 plus cosine x. Now, let's, you can do this in general, of course, and get a general formula, and we'll have occasion to use that next week. But for now, why don't we concentrate on the most interesting case, namely that of the linear equation with constant coefficient. That is, so let's look at the linear equation with constant coefficient, because that's the one that most closely models the conduction and diffusion equations. So what I'm interested in is, since this is of them all, probably the most important case is the one where p is a constant, because of its application to that, and many of the other, the bank account, for example, all of those would use a constant coefficient. So how is the thing going to look? Well, I'll use the cooling. Let's use the temperature model, for example. The temperature model, the equation will be dt dt plus kt is equal to, now notice on the right-hand side, this is a common error, you don't put TE, you have to put KTE, because that's what the equation says. If you think units, you won't have any trouble. Units have to be compatible on both sides of a differential equation, and therefore whatever the units were for capital KT, I'd have to have the same units on the right-hand side, which indicates I cannot have KT on the left of the differential equation and just T on the right and expect the units to be compatible. That's not possible. So that's a good way of remembering that if you're modeling temperature or concentration, you have to have the K on both sides. Okay, let's do, now a lot of this we're going to do in our head now, because this is really too easy. What's the integrating factor? Well, the integrating factor is going to be the integral of K. The coefficient now is just K. P is a constant K. And if I integrate K dt, I get KT. And I exponentiate that, so the integrating factor is e to the KT. I multiply through both sides, multiply by e to the KT, and what's the resulting equation? Well, it's going to be, I'll write it in the compact form, it's going to be e to the KT times t, all prime. The differentiation now, of course, is with respect to the time, and that's equal to k t e, whatever that is, times e to the kt. This is a function of t, of course, the function of little time. Sorry, little t time. Okay, and now finally we're going to integrate. What's the answer? Well, it is e to the, so we're going to get e to the kt times t is, sorry, k little t, k times time times the temperature is equal to the integral of k te, I'll put the fact that it's a function of t inside just to remind you, e to the kt, and now I'll put the arbitrary constant. Let's put in the arbitrary constant explicitly. So what will t be? Okay, t will look like this finally. It will be e to the negative kt, that's on the outside. Then you will integrate. Of course, the difficulty of doing this integral depends entirely upon how this external temperature varies. But anyway, it's going to be k times that function which I haven't specified, e to the kt, plus c times e to the negative kt. Now, some people, many in fact, and almost always in the engineering literature, almost never write indefinite integrals because an indefinite integral is indefinite. In other words, this covers not just one function, but a whole multitude of functions which differ from each other by an arbitrary constant. So in a formula like this, there's a certain vagueness, and it's further compounded by the fact, I don't know whether to put whether the arbitrary constant is here. I seem to have put it explicitly on the outside the way you're used to doing from calculus. Many people therefore prefer, and I think you should learn this, to do what is done in the very first section of the notes called definite integral solutions. They like, if there's an initial condition saying that the internal temperature at time 0 is some given value, what they like to do is make this thing definite by integrating here from 0 to t and making this a dummy variable. You see what that does is it gives you a particular function, whereas it was a, I'm sorry I didn't put in the dt one, minus 2. What it does is that when time is 0, all this automatically disappears, and the arbitrary constant will then be, well, it's t, so in other words, c times this, which is 1, is then equal to t. In other words, if I make this 0, then I can write c as equal to this arbitrary starting value. Now, when you do this, the essential thing, and we're going to come back to this next week, but right away, that because k is positive, I wanted, since I emphasized that so much at the beginning of the period, I want to conclude by showing you what its significance is. This part disappears because k is positive, the conductivity is positive, this part disappears as t goes to 0. This goes to 0 as t goes to infinity. So this is the solution that remains. This, therefore, is called the steady state solution, the thing which the temperature behaves like as t goes to infinity. This is called the transient because it disappears as t goes to infinity. It depends on the initial condition, but it disappears, which shows you that in the long run, for this type of problem, the initial condition makes no difference. The function behaves always the same way as t goes to infinity. The topic for today is how to change variables. So we're talking about substitutions in differential equations or changing variables. That might seem like a sort of fussy thing to talk about in the third or fourth lecture, but it isn't. The reason is that so far you know how to solve two kinds of differential equations, two kinds of first-order differential equations. The one where you can separate variables and the linear equation that we talked about last time. Now, the sad fact is that in some sense those are the only two general methods there are. That those are the only two kinds of equations that can always be solved. Well, what about all the others? The answer is that to a great extent all the other equations that can be solved, the solution is done by changing the variables in the equation to reduce it to one of the cases that we can already do. Now I'm going to give you two examples of that, two significant examples of that today, but ultimately, as you'll see, the way the equations are solved is by changing them into a linear equation or an equation where the variables are separable. However, that's for a few minutes. The first change of variables that I want to talk about is an almost trivial one, but it's the most common kind there is, and you've already had it in physics class. But I think it's so important in the science and engineering subjects that it's a good idea even in 1803 to call attention to it explicitly. So in that sense, the most common change of variables is the one simple one called scaling. So again, the kind of equation I'm talking about is a general first-order equation. And scaling simply means to change the coordinates, in effect to change the axes, to change the coordinates on the axes, to scale the axes, to either stretch them or contract them. So what does the change of variable actually look like? Well, it means you introduce new variables where x1 is equal to x times something or times a constant. I'll write it as divided by a constant, since that tends to be a little bit more the way people think of it, and y the same. So the new variable y1 is related to the old one by an equation of that form, so a, b constants. So those are the those are the equations. Why does one do this? Well, there are a lot of reasons, but maybe we could list them. For example, could be changing units. That's a common reason in physics. Changing the units that are used, you'd have to make a change of coordinates of this form. Perhaps an even more important reason is to sometimes it's used to make the variables dimensionless. In other words, where the so that the variables become pure numbers with no units attached to them. Since you're well aware of the tortures involved in dealing with units in physics, the point of making variables dimensionless, I don't have to sell that. Dimensionless, i.e. no units, without any units attached. It's just, it represents the number 3, not 3 seconds or 3 grams or anything like that. And the third reason is to reduce or simplify the constants. Reduce the number or simplify the constants in the equation. Reduce their number is self-explanatory. Simplify means make them less, either dimensionless also, or if you can't do that, at least less dependent upon the critical units than the old ones were. Let me give you a very simple example which will illustrate most of these things. It's the equation, it's a version of the cooling law which applies at very high temperatures, and it runs So it's like Newton's cooling laws, except it's the internal and external temperatures are very, what's important is not the first power as in Newton's law, but the fourth power. So it's a constant, and the difference is now it's the external temperature, which just, so there won't be so many capital T's in the equation, I'm going to call M, to the fourth power minus T to the fourth power. So T is the internal temperature, the thing we're interested in, and M is the external constant, which I'll assume now is a constant external temperature. So this is for valid if a big temperature differences, Newton's law breaks down and one needs a different one. Now, you're free to solve that equation just as it stands if you can. There are difficulties connected with it because you're dealing with fourth powers, of course. But before you do that, one should scale. How shall I scale? Well, I'm going to scale by relating T to M. So the new variable I'm going to use is T1 equals T divided by M. This is now dimensionless because M, of course, has the units of temperature, degrees Celsius, degrees absolute, whatever it is, as does T, and therefore by taking the ratio of the two, it now becomes, there are no units attached to it. So, so this is dimensionless. Now, how actually do I change the variable in the equation? Watch this. It's an utterly trivial idea and utterly important. Don't slog around doing it this way, trying to stuff it in and divide first. Instead, do the inverse. In other words, write it instead as T equals MT1. The reason being that it's T that's facing you in that equation, and therefore T that you want to substitute for. So let's do it. The new equation will be what? Well, dt, since this is a constant, the left-hand side becomes dt1 dt times m equals k times m to the fourth minus m to the fourth t1 to the fourth. So I'm going to factor out that m to the fourth and make it 1 minus t1 to the fourth, okay? Now, I can divide through by m and get rid of one of those, and so the new equation now is dt1 dt, the time, is equal to, now I have km cubed out front here. I'm going to just give that a new name, k1. Essentially, it's the same equation. It's no harder to solve, nor and no easier to solve than the original one. But it's been simplified slightly. For one thing, it looks better. It looks better. Let's to compare the two, I'll put this one up in green, and this one in green too, just to convince you it's the same, indicate that it's the same equation. Notice, so T1 has been rendered, is now dimensionless, so I don't have to even ask when I solve this equation, oh, please tell me what the units of temperature are. What kind of, how are you measuring temperature? It makes no difference to this equation. K1 still has units. What units does it have? It's been simplified because it now has the units of, since this is dimensionless and this is dimensionless, it has the units of inverse time. So K1, whereas it had units involving both degrees and seconds before, now it's inverse time as its units. And moreover, there's one less constant, so one less constant in the equation. It just looks better, in short. This business, I think you know that K1, the process of forming K1 out of K1 out of km cubed is called lumping constants. I think they use that standard terminology in physics and in engineering courses. You try to get all the constants together like this, and then you lump them. They are lumped for you, and then you just give the lump a new name. So that's an example of scaling. Watch out for when you can use it. For example, it would have probably been a good thing to use in the first problem set when you were handling this problem of drug elimination and hormone elimination and production inside of the thing. You could lump constants in, as was done to some extent on the solutions, to get a neater looking answer, one without so many constants in it. Okay, now let's now go to serious stuff, where we're actually going to make changes of variables which we hope will render unsolvable equations suddenly solvable. Now, I'm going to do that by making substitutions, but it's, I think, quite important to watch out that there are two kinds of substitutions. There are direct substitutions. That's where you introduce a new variable. I don't know how to write this on the board. I'll just write it schematically. So the new, it's one which says that the new variable is equal to some combination of the old variables. The other kind of substitution is inverse. It's just the reverse. Here you say that the old variables are some combination of the new. Now, often you'll have to stick in a few old variables too, but the basic, it's what appears on the left-hand side. Is it a new variable that appears on the left-hand side by itself, or is it the old variable that appears on the left-hand side? Now, right here we have an example. If I did it as a direct substitution, I would have written T1 equals T over M. That's the way I define the new variable, which of course you have to do if you're introducing it. But when I actually did the substitution, I did the inverse substitution. Namely, I used T equals T1, M times T1. And the reason for doing that was because it was the capital T's that faced me in the equation, and I had to have something to replace them with. Now, you've seen this already in calculus, this distinction, but that might have been a year and a half ago. Just let me remind you. Typically in calculus, for example, when you want to do this kind of integral, let's say x times the square root of 1 minus x squared dx, the substitution you would use for that is u equals 1 minus x squared, right? And then you'd calculate, and then you'd observe that the x dx more or less makes up du apart from a constant factor. So this would be an example of direct substitution. You'd put it in and convert the integral into an integral in u. What would be an example of inverse substitution? Well, if I take away the x and ask you instead to do this integral, then you know that the right thing to do is not to start with u, but to start with the x and write x equals sine or cosine u. So this is a direct substitution in that integral, but this integral calls for an inverse substitution in order to be able to do it. And notice they look practically the same, but of course, as you know from your experience, they're not. They're very different. Okay, so I'm going to watch for that distinction as I do these examples. And the first one I want to do is an example of a direct substitution. So it applies to an equation of the form y prime equals, there are two kinds of terms on the right-hand side. A of x, let's use P of x. P of x times y plus Q of x times any power whatsoever of y. Well, notice, for example, if n were 0, what kind of equation would this be? Y to the n would be 1, and this would be a linear equation, which you know how to solve. So n equals 0, we already know how to do, so let's assume that n is not 0, so that we're in new territory. Well, if n were equal to 1, you could separate variables, so that too is not exciting, but nonetheless, it will be included in what I'm going to say now. If n is 2 or 3, or n could be 1/2, so n anything. Even 0 is all right, it's just silly. Any number. Could be negative, n equals -5, that would be fine also. This kind of equation, to give it its name, is called the Bernoulli equation. Named after which Bernoulli, I have not the faintest idea. There were, I think, 3 or 4 of them, and they fought with each other, but they were all smart. Now, the key trick, if you like, method to solving any Bernoulli equation, let me call one other thing I should call out. Most important is what's missing.